In 2003, a team of astronomers peering into the distant reaches of our solar system stumbled upon a remarkable discovery, a dwarf planet lurking in the Kuiper Belt, later christened Sedna. At the time, it held the title of the most distant known object orbiting our sun, a solitary sentinel in the cosmic wilderness. This wasn't just another rock floating in space, it was a revelation, a key that unlocked a cascade of questions and reshaped our understanding of the solar system's outer fringes. Sedna's discovery sent shockwaves through the astronomical community, and its implications were nothing short of revolutionary. For one, it played a pivotal role in dethroning Pluto from its long-held status as the ninth planet. Sedna's existence hinted that the Kuiper Belt, a vast icy ring beyond Neptune, wasn't just a cosmic afterthought, but a treasure trove teeming with secrets waiting to be unearthed. More tantalizing still, Sedna reignited an age-old debate that had simmered since the 19th century. Could there be a mysterious ninth planet hiding in the shadows, pulling strings from afar? The evidence was compelling. Out there on the ragged edge of the solar system, something massive seemed to be meddling with the orbits of smaller celestial bodies. These objects, scattered across the Kuiper Belt, weren't behaving as expected. Their paths curved and twisted, deviating from the tidy trajectories one might predict. Imagine a flock of birds suddenly veering off course, all nudged by an unseen wind. The orbits of these distant wanderers were stretched into elongated ovals, and curiously, they all tilted in the same direction, skewed by the same precise angle. This wasn't random chaos, it bore the fingerprints of a gravitational puppeteer. Enter Michael Brown and Konstantin Batygin, two astronomers who've staked their reputations on cracking this cosmic mystery. They're convinced that this unseen influencer is none other than the elusive Planet 9, a world perhaps 10 times Earth's mass, with a diameter 2 to 4 times our own, lurking in the darkness beyond Neptune. For Brown and Batygin, Sedna wasn't just a discovery, it was a breadcrumb leading to a prize that could define their careers. Their calculations, based on the peculiar dance of Sedna and a handful of other Kuiper Belt objects, suggest a planet so massive it warps the fabric of space around it, tugging at everything in its reach, but not everyone sold on the idea of a planet. Some scientists propose a more exotic suspect, a primordial black hole. Now, don't picture the colossal, star-gobbling behemoths at the hearts of galaxies. This would be a tiny, dense relic from the dawn of time, perhaps no bigger than a bowling ball or even a tennis ball, yet packing a gravitational punch far out of proportion to its size. These hypothetical objects, dubbed primordial black holes, could be sprinkled across the universe like cosmic Easter eggs, remnants of the Big Bang's chaotic birth. The notion of primordial black holes first flickered to life in the 1960s, thanks to Soviet physicists Yakov Zeldovich and Igor Novikov. They imagined a universe just seconds old, a searing, dense speck born from the Big Bang some 13.7 billion years ago. In those fleeting moments, the cosmos was a cauldron of unimaginable heat and pressure, a primordial soup where the rules of physics were still taking shape. Then came a pivotal split. Gravity peeled away from the other fundamental forces, electromagnetism, the weak nuclear force, and the strong nuclear force, ushering in an era known as the Planck epoch. This epoch lasted a mere fraction of a second, a blink in cosmic terms, yet it set the stage for everything that followed. The universe was still microscopic, measured in Planck lengths, unfathomably small units, but it brimmed with potential. As it expanded and cooled, pockets of extreme density emerged amid the turmoil. In these hotspots, gravity could have clumped matter so tightly that it collapsed into tiny black holes, each a seed of destruction sown in the universe's infancy. Stephen Hawking picked up this thread in 1971, weaving it into a richer tapestry. He calculated that primordial black holes might range in mass from modest asteroids to hulking planetoids, or even several times the heft of our Sun. Unlike their stellar-born cousins, which form from the corpses of massive stars, these primordial oddities could be any size, their origins tied not to stellar death, but to the Big Bang's raw energy. The smallest ones, Hawking reasoned, would be long gone by now, evaporating in bursts of radiation, a phenomenon now called Hawking radiation. This self-accelerating process ends in a flash, though no one's caught such a fireworks show in the sky. Larger primordial black holes, however, could still linger. Those in the mid to heavy range, say asteroid-sized or planetoid-shaped, might lack the spin of stellar black holes, making them trickier to spot. They don't gobble up matter with the ferocity needed to form glowing accretion disks, the telltale halos that often betray their presence. Instead, they might reveal themselves subtly, bending light through gravitational lensing, a cosmic magnifying glass effect that warps the paths of distant stars' rays. Hawking speculated that our galaxy, the Milky Way, could be peppered with these ancient relics. If they formed in droves during the Big Bang's early chaos, some should still haunt the cosmos today. Yet, despite decades of searching, no one's nabbed definitive proof. Primordial black holes remain a tantalizing what if, a hypothesis dangling just out of reach. If they do exist, though, they could unlock some of cosmology's thorniest puzzles, starting with dark matter. Dark matter, that invisible glue holding galaxies together, accounts for about 25% of the universe's mass energy budget. It doesn't glow, reflect, or radiate, yet its gravitational pull shapes the cosmos. In 1994, Russian astrophysicists Pavel Ivanov, Pavel Naselsky, and Igor Novikov floated a bold idea. What if primordial black holes, with masses around a tenth of our sun's, were plentiful enough to explain this unseen heft? Even if they're not the whole story, these compact enigmas could contribute significantly to the dark matter tally, offering a concrete candidate for a mystery that stumped scientists for generations. But the intrigue doesn't stop there. Primordial black holes might also explain stranger phenomena, like the merging of black hole pairs. Stellar evolution models struggle to account for such duos. If two massive stars birth black holes, one typically collapses first, siphoning material from its partner and stunting its growth. Yet we've detected these mergers via gravitational waves. Could they be primordial black holes, never stars to begin with, drifting together since the universe's youth? Or take the supermassive black holes squatting in galactic cores. Conventional wisdom says galaxies birthed these giants, feeding them over eons. But what if it's the other way around? What if primordial black holes, seated in the Big Bang, acted as gravitational anchors, gathering matter and sparking galaxy formation? Quasars, blazing beacons powered by supermassive black holes, have been spotted at distances implying they existed just 12.9 billion years ago, when the universe was barely a billion years old. Their staggering masses, hundreds of times greater than the Milky Way's central black hole, defy easy explanation. How could they grow so vast so fast? Here's where primordial black holes shine as cosmic accelerators. Picture them as Big Bang seedlings, their gravity hastening the clumping of matter into stars and galaxies. The youngest galaxies we've observed formed a mere 400 million years after the Big Bang. Far too quickly, some argue, for standard star formation alone. A scattering of primordial black holes could have turbocharged the process, their pull sculpting the early universe into the sprawling tapestry we see today. Back in the Kuiper Belt, Brown and Bataillegan's Planet 9 hunt echoes these grander questions. Their evidence hinges on Sedna and 6 other far-flung objects, whose orbits are aligned too neatly to be mere coincidence. These bodies trace elliptical paths, skewed perpendicular to the solar system's plane, as if herded by a massive shepherd. The duo's math points to a Neptune-sized world, or perhaps a black hole the size of a grapefruit, with a mass 10 times Earth's. Light bending near its suspected location adds fuel to the black hole theory, though a snapshot from a telescope remains the holy grail. Deep within the enigmatic heart of a black hole lies a puzzle that defies comprehension: the singularity. This infinitely dense point twists the fabric of space-time into a knot so tight that our logical frameworks unravel. Worse still, it flouts some of the universe's most sacred rules. The thorniest issue revolves around how black holes handle information, the quantum blueprints describing everything they devour. Physicists cling to a bedrock principle: information cannot, must not, be destroyed. Yet when a singularity swallows it whole, that's precisely what seems to happen. This conundrum, known as the black hole information paradox, is a cosmic riddle of monumental stakes. But let's hold off on that for a moment and dive into something equally mind-bending: the Planck star. Picture a Planck star as a daring alternative to the singularity, a theoretical twist born from the Big Bounce hypothesis. This isn't your standard cosmic tale of a one-and-done Big Bang. Instead, imagine the universe as a phoenix, endlessly rising from its own ashes in a cycle of collapse and rebirth. The Big Bang we know? It might just be the latest chapter, not the opening scene. Before our universe stretched into being, another could have existed, one that ballooned to its limits, then crumpled under its own weight, only to explode anew. It's reincarnation on a galactic scale, a story of perpetual renewal. Curious for more? There's a video diving into this cosmic loop. Check the link up top on the right. Here's how it plays out. The universe expands until it hits a tipping point, a moment when the average density of space-time reaches a critical threshold. Then the tide turns. Expansion halts and collapse begins, squeezing all matter into a super-dense state, something eerily akin to a black hole's singularity. But the Big Bounce theory doesn't let it end there. When matter compresses to the Planck scale, the tiniest conceivable unit in physics, an extraordinary rebound kicks in. This isn't mere speculation. It's a lens that could reshape how we view black holes entirely. What if the collapse of a stellar core doesn't doom it to an infinitely dense singularity, as we've long assumed for stellar mass black holes? Suppose instead that quantum pressure steps in, halting the plunge. Think of it like the force that keeps an electron from crashing into an atom's nucleus, a subtle but mighty resistance. This isn't as wild as it sounds. After all, neutron degeneracy pressure can stall a star's collapse, leaving behind neutron stars or pulsars, while electron degeneracy does the same for sun-sized stars, birthing white dwarfs. Scale that up and quantum effects might stop matter from hitting infinite density, not just in stars but across the cosmos. In this grander picture, the Big Bounce doesn't wait for the universe to shrink to Planck length. It triggers when the energy density of matter hits Planck scales, the densest possible state in physics. The universe doesn't just teeter on the edge, it springs back, a cosmic trampoline launching a new era. For black holes, this could mean singularities aren't the endgame. Instead, they harbor Planck stars, compact quantum-defying objects that rewrite the script. So, what would a Planck star look like to us? The clue's in the name. These entities would be staggeringly small, dwarfing even an atom, squeezed down to Planck dimensions. But their real magic lies in time. Time, that relentless river, doesn't flow the same for everyone. On Earth's surface, it ticks slightly differently than in low orbit, a subtle shift. Near massive stars, planets, or black holes, the difference grows stark. As light nears a black hole's event horizon, the boundary beyond which nothing escapes, time slows to a crawl. Inside, some of the brightest minds speculate it might freeze altogether. From the outside, though, you'd never guess. It's a head-scratcher, so let's borrow a scene from Interstellar to simplify. Remember the water planet orbiting a black hole? An hour there stretched into decades elsewhere. The first astronaut to land might have touched down 10 years prior, yet for her, mere hours passed before the next crew arrived, her beacon still blinking, though her transmissions had long faded. A Planck star might live a similar dual life, a fleeting instant in its own frame, crossing its tiny expanse at light speed, yet enduring for millions or billions of years to an outsider, coexisting with the black hole itself. Perhaps it's not a star in the classic sense, more a burst of light unleashed as the black hole dies. This brings us full circle to the information paradox. Replace the singularity with a Planck star, and the problem might dissolve. Black holes gradually shed mass via Hawking radiation, a slow leak of energy over eons. Eventually, the Planck star within could expand, releasing all the trapped information in a final flourish. Some theorists even suggest these stars emit a detectable quantum gravitational signal, with wavelengths around 10 to 14 centimeters, tiny enough to hint at their presence in gamma-ray signatures. Could we have already glimpsed one, misfiled in the data? Carlo Rovelli, a co-creator of the Planck star idea, thinks it's testable. The spectra of black hole explosions, he argues, shift based on distance from Earth. Match those patterns to fast radio bursts, and the theory might hold water, or it might not. So far, no smoking gun, but the universe loves a good tease. Imagine standing on the edge of a cosmic precipice, peering into the abyss of a dying black hole. As its mass dwindles, the Planck star inside swells, a ticking clock counting down to revelation. What might we see? A flicker of gamma rays, perhaps, or a whisper of light from a realm where time itself bends. Rovelli's bet isn't just a hunch, it's a challenge to scour the skies with tools like the Fermi Gamma Ray Space Telescope, hunting for those telltale bursts. Fast radio bursts, those enigmatic blips we've caught in recent years, could be Planck stars winking at us from the void. Or they could be something else entirely, cosmic static teasing our curiosity. Speaking of teases, don't confuse Planck stars with primordial black holes. Those Big Bang relics are a different beast, tied to Planck length, not energy density. A video on those? Maybe, if you clamor for it in the comments. For now, let's pivot to another cosmic oddity that's equally spellbinding: boson stars. These aren't your twinkling night sky fixtures, they're hypothetical marvels that stretch the imagination. To grasp boson stars, we need a quick dip into particle physics. Don't worry, we'll keep it light. The Standard Model splits the universe's building blocks into two camps: fermions, the stuff of matter, and bosons, the couriers of forces. Fermions are loners, one per slot in space, while bosons are party animals, piling up without limit. We know 6 elementary bosons, like the W and Z bosons of weak interactions, which flip particles from one type to another. But the headliner is the Higgs boson, discovered amid fanfare at CERN. It's the VIP that gifts particles their inertial mass, the kind that resists a shove, not the gravitational pull. A quantum theory marrying inertia and gravity, still a pipe dream. Now, imagine a stable swarm of bosons, bound by their own gravity into a self-sustaining system. That's a boson star, a cosmic outlier unlike any star we know. They might mimic a sphere, like their fiery cousins, but some theorists picture them flattening into a colossal donut under centrifugal spin. Trouble is, none of the bosons we've pinned down, like the Higgs, fit the bill. They're either too unstable or massless to clump into stars. But yet is the key word. Undiscovered bosons like the elusive graviton, hypothetical carrier of gravity, could change the game. Gravitons might boast both mass and stability, the perfect recipe for boson stars. A graviton deep dive. Drop a yes below if you're game. If gravitons exist, boson stars could have burst into being post-Big Bang, collapsing from primordial gravity wells. Unlike fermion-based stars, they wouldn't shine. They'd be transparent, ghostly orbs adrift in space. Their only giveaway? A gravitational tug strong enough to bend light or nudge orbits. When they grow too bloated, they might collapse, blasting out radio photons, a clue that sparked the theory. But without a known boson to build them, they stayed off the radar until tools like LIGO and Virgo, gravitational wave hunters, came online. Boson stars' waves would ripple differently than those from stellar giants, offering a shot at detection. Picture a boson star drifting silently through the cosmos, a shadow among shadows. Its collapse wouldn't be a fiery supernova, but a quiet implosion, a radio whisper echoing across light years. LIGO's sensors might catch that tremor, a vibration distinct from the violent clashes of neutron stars or black holes. And if gravitons are real, these stars could be legion, born in the Big Bang's afterglow, clustering in the dark corners of galaxies. Some speculate they'd swarm near galactic centers, masquerading as the supermassive black holes we've pinned there. Others see them as lone wanderers, bending starlight in subtle arcs we've yet to decode. Where to look? The cosmos is vast, but galactic cores are prime suspects. A boson star there could explain the wild antics of active galactic nuclei, those blazing hubs of energy. Or maybe they're scattered across the void, silent until they burst. Unlike Planck stars tied to black hole deaths, boson stars could stand alone, relics of a universe still spilling its secrets. Detecting them might mean sifting through gravitational wave data, teasing apart the hum of the cosmos for a note no one's heard before. Imagine the thrill. Pinpointing a boson star's echo could unveil new particles, rewriting physics from the ground up. The universe isn't done surprising us. Planck stars, boson stars, quark stars, they're paper dreams for now, but the evidence mounts. Fast radio bursts, gravitational ripples, gamma-ray flickers, each could be a breadcrumb to the next big find. Once exoplanets and galaxies awed us. Now, they're old news to a skeptical age. Yet the cosmos keeps its aces up its sleeve, daring us to peek. Will Planck's stars solve the information paradox? Could boson stars anchor galaxies? The answers hover just out of reach, but the hunt, fueled by math, telescopes, and sheer wonder, presses on. Consider the stakes. A Planck star's discovery could upend our view of black holes, proving information endures beyond the event horizon. Boson stars might crack gravity's code, linking it to the quantum realm. Each breakthrough would ripple beyond science, stirring philosophy and imagination alike. Are we on the cusp of spotting one? Picture a telescope catching a gamma flicker, or LIGO tracing a wave to a donut-shaped ghost. The universe doesn't yield easily, but its whispers grow louder. What's your bet on the next revelation? Let's hear it. Imagine a cosmic riddle so elusive it's been dubbed the invisible puppeteer of the universe. Dark matter. This mysterious substance doesn't glow, flicker, or whisper its presence through light, yet it wields a gravitational pull that keeps galaxies from spinning apart. Scientists have chased its trail for decades, pinning their hopes on everything from exotic particles to unseen dimensions. But what if the answer, or at least part of it, lies in something as strange and captivating as a boson star? Yes, those hypothetical orbs of pure bosons might just be a piece of the dark matter puzzle, and a recent discovery has sent ripples of excitement through the astronomical community. It all started with a gravitational wave, a faint tremble in the fabric of space-time detected in an event tagged GW19521. When the signal first washed over Earth's observatories, experts buzzed with the obvious guess. Two massive black holes, weighing in at 66 and 85 times the Sun's mass, had smashed into each other in a cataclysmic dance. The idea fit neatly. Black holes are the heavyweight champs of cosmic collisions after all. But as researchers dug deeper, poring over the data with furrowed brows and humming computers, cracks appeared in that story. The numbers didn't quite align. Something was off. Then came a bold twist. What if this wasn't a black hole tango at all, but a clash of boson stars, ghostly spheres woven from ultralight bosons? Now, boson stars aren't your average celestial celebrities. They don't blaze with nuclear fire or twinkle in the night sky. Picture them instead as ethereal bubbles lacking a solid core, transparent to light, and utterly invisible to the naked eye. Sound familiar? That description could double as a black hole's resume. Both are compact, both wield gravity like a maestro, and here's the kicker. Some boson stars might even sport a shimmering ring of plasma, a glowing donut encircling a dark heart. It's eerily similar to the accretion disk that swirls around a black hole, painting a portrait of cosmic mimicry that's hard to ignore. From millions of light years away, could we really tell them apart? At first glance, you'd think not. Black holes have a defining trait: the event horizon, that invisible line where light and matter check in but never check out. Boson stars, though, lack this boundary. No trapdoor to oblivion, just a dense, gravity-warped blob. But distinguishing them isn't a hopeless quest. Scientists turned to a high-tech crystal ball, computer simulations. They modeled the dynamics of that plasma ring around a boson star and pitted it against the behavior of a black hole's accretion disk. The results? A revelation. The shadow cast by a boson star, a silhouette carved out by its gravity-bending light, is noticeably smaller than the gaping maw of a black hole shadow of the same mass. This shadow game became a cosmic litmus test. Take GW9521's aftermath. Researchers calculated the mass of the colliding objects and clocked the speed of the gas swirling around them. The shadow loomed too large, too pronounced to belong to a boson star. Verdict: black holes, not boson imposters. But here's where it gets juicy. This doesn't slam the door on boson stars. It just means we've got a sharper tool to spot them. What if some of the black holes we've cataloged, those dark titans we've crowned as cosmic royalty, are secretly boson stars in disguise, pulling a fast one on our telescopes? The implications are dizzying. If boson stars are real, they could be dark matter's missing link. We've long pictured dark matter as a shadowy sea of particles, too aloof to shine yet heavy enough to anchor galaxies. Boson stars fit the bill. Unseen, gravitationally potent, and potentially numerous. Some theorists go further, whispering that these stars might be forged from gravitons, those still undiscovered messengers of gravity. If true, it's a game changer. Either dark matter isn't what we thought, or gravity itself is tangled up in its essence. Suddenly, the universe feels less like a solved equation and more like a thriller, with a twist ending still unwritten. Let's rewind and paint the scene. The GW19521 signal wasn't just a blip, it was a cosmic drum roll. Detected by the Laser Interferometer, Gravitational Wave Observatory, LIGO, and its partner Virgo, it rippled through space-time like a pebble dropped in a pond. At first, the black hole theory held sway because it's the go-to playbook for such events. Two stellar corpses, born from exploded stars, spiral inward over eons, their orbits tightening until they merge in a flash of warped reality. But the masses, 66 and 85 solar masses, raised eyebrows. Stars massive enough to birth such black holes should have shed too much material in their fiery youth to fit the profile. Enter the boson star hypothesis. No stellar origins needed, just a swarm of bosons clumping together in the universe's early chaos. To test this, scientists didn't just lean on gravitational waves. They zoomed in on the aftermath, the light and gas left behind. Black holes often leave a blazing trail as they gobble up nearby matter, their accretion disks glowing like neon signs. Boson stars, though, play it cooler. Their plasma rings, if they have them, shimmer with a subtler flare. Simulations showed that a boson star's shadow wouldn't stretch as wide, its gravitational lens less distorted than a black hole's. When GW19521's data rolled in, the shadow's size tipped the scales. It wasn't a boson star's delicate footprint, it was the hulking mark of a black hole. But don't write off boson stars yet. This one case doesn't bury the idea, it sharpens our focus. Imagine a sky dotted with these invisible mimics, some masquerading as black holes, others lurking undetected. If they're out there, they could be plentiful, relics from the Big Bang, forged when gravity first flexed its muscles, and if they're gravitons in disguise. That's a plot twist that could rewrite physics. Dark matter might not be a swarm of particles, but a legion of boson stars, their gravity weaving the cosmic web we've puzzled over for a century. The chase is on. LIGO and Virgo keep their ears to the universe, listening for the next ripple. Telescopes scan for shadows that don't quite fit the black hole mold, subtle clues in the bending of starlight or the hum of radio waves from a collapsing boson star. Each observation peels back another layer, teasing us closer to the truth. Are boson stars the dark matter we've sought? Or just one thread in a tapestry of unknowns? Maybe they're both, partners in a cosmic conspiracy, hiding in plain sight. This isn't the end of the story, it's the opening act. The universe loves a good mystery, and boson stars are its latest cliffhanger. They challenge us to rethink what we know, to peer beyond the obvious and question the shadows. Could they unlock dark matter's secrets? Might they bridge gravity and the quantum world? The answers are out there, twinkling in the void, waiting for us to catch up. So buckle up. The most thrilling chapters lie ahead. Picture yourself stargazing on a clear night, wondering if those unseen forces are boson stars winking back. Excited? You should be. The cosmos is a stage and the spotlight's just warming up. Stay curious, keep exploring, and let's unravel this together, because the best is yet to come.